In this video, we shall explore a less trivial situation where we shall make a linear model using the black box approach. We shall again work with that spring example, but this time we shall use two different types of spring. Now both the springs are effectively very similar, made out of same kind of material, same material, but they have some difference which we cannot ignore. That is something that we cannot just sweep under the rug of random error. Now this scenario is a very common one that we experience in practice, where you have to work with certain units or systems like plots or patients, but you do not have enough of those systems in one place. For example, you need to work with lots of patients, and one single hospital will not be able to provide that many patients, so you spread out your research over multiple hospitals. Then each hospital will bring its own unique factors. They may not be the most important factor, they might become important, so only the study can tell that, but at least your primary goal is not to study the difference of the different hospitals. But still, those differences may not be ignored. Similarly here, I will pretend that this thing, say, comes from one lab and this thing comes from another lab. They have same types of spring. However, you can see that here the length is less than the length here. So there is some difference. It's not random difference. Our aim is not to investigate the difference of length. Our aim is to investigate the behavior, elastic behavior of the spring. With respect to that, they are both same material, same geometry, same radius, etc., etc. Now, how do you deal with this thing using a black box? The solution may not be that obvious. In this case, the particular thing that we use will be this black box. Now, this black box has, again, that spring, one input, that is the weight, and the usual output, that is this length. However, it has got another input, that is the lab. Now, observe this carefully. The lab is not what you would naturally think of as input. It is not that there is something called a spring to which you applied an effect of lab. Lab is already there. So this spring comes from, say, lab 2 and that spring comes from lab 1. But when we want to make the black box, we consider this spring, what we have written inside that green box, that is the abstract notion of spring, what we want to study. Now we have different types of springs, so that also is actually an input. So in this case, we have got two inputs, weight, that's a covariate, a continuous one, and lab, that is a categorical input, a factor. And the output is, as before, just our length. So you hang different weights in lab 2, you hang different weights in lab 1, you make the measurements, and as a result, from the two labs, you will get two sets of data. Say you get this from lab 1, say lab 1, and this you get this from lab 2. So you have different weights, and you have got different weights, and you have got different lengths. All these things come from lab 1. Similarly, all these things come from lab 2. Observe that the two labs may or may not use the same set of weights. For example, here I can see 1.5 has been used in both the cases. Of course, the elongations are different, the lengths are different because they are working with springs that started with different initial lengths. Some of the weights, in fact, most of the weights are different from this lab to that lab. In this case, one particular weight has been repeated. So it is a repeated measure experiment, which is the most common thing in practical scenarios, where you hang the same weight a multiple number of times and take different measurements just to get an idea about the effect of the random error. So you get one Excel file like this from one lab and another Excel file like this from this lab. Now the question is, how do we combine them? Because remember, R or any other software needs one single data set to do the analysis, not two different data sets. So how do I merge them?